In 3.1, we talked about quadratic functions. So we had something like f of x equals, maybe 4x squared plus 3x minus 8 or something like that, okay? And we said that when we have an x squared, it makes a parabola shape. And since our a value is positive here, it would be a smiling parabola. And we talked about how we could find, a max or a min, find a vertex, and those are some of the key features that we looked at there. Finding the vertex, finding the x-intercepts, y-intercepts, etc. Okay, in 3.2, we're going to take it a step further. What if this exponent on the x was higher than 2? What if it was 3, or 4, or 5, or 6, or some even higher number? Okay, we call those polynomial functions. That prefix poly just means many. Okay, so you can have many exponents. It can be higher than 2. So our official format of a polynomial function is some number a, okay? It could have been 4 like it was here on this quadratic. It could be 17. It could be negative 8. It could be a decimal like 3.4, whatever, okay? So I'm just going to make it 8 times x to the whatever number. They put an n to represent whatever exponent. I'm going to put a 5, okay? Does not really matter how high that number is. Then we keep on adding more and more terms. I'm going to put plus, and this next number, they call it a of n minus 1. They're just saying some value. It does not have to be 8 like it was before. It could be 7 or 6 or 2.5 or negative 4 or whatever number, followed by another x. And notice the exponent on this one. The exponent here is n minus 1. So that's saying whatever exponent you had on the first term, drop it by 1. So this might be 2.5x to the 4th. And then I keep on going with more and more terms. So whatever number I want in front of the x, so minus 5, x to the, and I'm going to have to drop it by 1 for my exponent. So I had an exponent of 5, exponent of 4, next would be an exponent of 3, and then an exponent of 2, and then an exponent of just 1, or I'm just going to keep that as a plain x. So I dropped my exponent by 1 until I got to just x to the 1, and I didn't put the 1, but it's implied, plus whatever number you want, x to the 0. Now think about it. If I have an x to the 0, then there's not really any x's there at all, which is what we had. Okay? So this is just saying, hey, you can start your exponent at whatever number you want and work your way down until you don't have any variables at all. Okay? All right. Couple of examples here. These are all polynomial functions, and then these are not polynomial functions, and let's talk about why, okay? One thing I need to mention is the term degree. The degree is the biggest exponent. So when we had a quadratic, our biggest exponent was 2. So we said, hey, if there's an x squared, the exponent is 2. If the degree is 2, then you're dealing with a quadratic. Notice this one I made up right here, my biggest exponent was 5. So the degree of this polynomial function is 5, okay? All right, so these on the left are all polynomial functions. What is this one's degree? It's a degree 4. Now notice they chose to start this one with an x to the 4th. It's missing the x to the 3rd. So basically the x to the 3rd part had a coefficient of 0. The x to the 2nd part had a coefficient of 0. The plain x had a coefficient of 0, and then they had their constant of 3 at the end. So it's okay to be missing pieces, and they can have coefficients of 0, but you should put them in decreasing order when possible. Okay, h of x. Notice they have not put these in the order that we would prefer. We would prefer to put the x to the 3rd first, and then the 2x squared, and then the plain x, and then the constant of 2. Okay, so once we have them in our descending order, it's a little bit easier to see that the degree of this one is 3. That's our biggest exponent. K of x, if you notice it does not have any x's. We could, if we wanted, put an x to the 0 on the end. You don't have to, you don't need it, but if it bothers you to not see any x's, you could think about it as an x to the 0, which means our degree is 0. And then this last one, okay, this one's kind of tricky. It does not look like the polynomial form that we've been working with so far. But what we could do is FOIL out x minus 1 times x minus 1. That's what the squared means. We could FOIL that out. If we did that, we'd have x squared minus x minus another x, which would be a minus 2x, and then the negative 1 times negative 1 is positive 1. Then we could distribute the n to the third, and that would give us, x to the third. X to the third times x squared would be x to the fifth. X squared times negative 2x would be negative 2x to the fourth, and then x to the third times 1 would be plus x to the third. Okay, if we FOILed it all out, we would go, oh, hey, look, our biggest exponent was 5, so our degree is 5. However, if we'd really thought about it, we could have figured out that the degree was 5 without doing all that multiplying out work. Notice that I had an x to the third, and then I had 2 sets of x minus 1. So if I realize I have an x to the third that would eventually have gotten distributed through an x squared, you would realize that that's 5 little x's that would eventually be multiplied together. So when it's written in factored form, this is called factored form right here, you can add up your exponents, and that would be your degree. Okay? All right, these were all polynomial functions on the left. On the right, these are not polynomial functions, okay? So their question to us is, what's wrong? Why can it not be written in that polynomial format that we talked about right up there at the top? Okay, well, in g of x, the problem is this radical, okay? We cannot have x's under a radical for polynomials. Now, they are square root functions. We could still graph it. It's just not a polynomial function. So what's wrong with that is that x is under a radical. Okay. In j of x right here, what's wrong with this one? Well, our exponents are not whole numbers. Remember, we said that you had to have, whole number exponents right here. So the exponents are not whole numbers. Now, I just want to point out, a while ago when we had this x under the radical, do you remember when we first started talking about radicals and our exponent rules in that last unit? And we said that if you raised a number to a 1/2 exponent to a fraction exponent, that really meant your numerator was the exponent and the denominator was your index number. So really, when we see these fraction exponents here, they're really just radicals. And we already said that radicals are not polynomial functions. Okay, so really J and G kind of have the same issue going on, and that's why they're not polynomials. Okay, M, the problem with this one is that we have an x in the denominator. If I didn't have that x minus 3, if it had just been x plus 1, then that would have been fine. It would have been polynomial. But we can't have x's in the denominator for it to be a polynomial function. Okay. And then same idea here. On this p of x, the x is in the denominator. Okay. Now, just so you know, I could have written this p of x. I could have called it 4 minus x to the negative 2. If you remember, a negative exponent really means stick it on the bottom. So when we see an x in the denominator, it's really a negative exponent situation. So negative exponents or x in the denominator are really the same thing, and that's why it's not a polynomial function. Okay? All right, so we know how to look at an equation and determine whether or not it's polynomial. Let's talk a little bit more about the graph and that term degree. We mentioned that the degree was the largest power of x. So in the general form, these first few on the left here were what we call general form. The degree is the greatest exponent. Okay. When we have them in factored form, n of x was in factored form, then the degree is the sum of the exponents. We said we could take that 3 and 2, the exponents there, and add them together to get our degree of 5. Okay, so just a reminder of that. When we're looking at a graph, okay, so for example, if I gave you these graphs, I did not give you the equation that produced these graphs. Some of them you may know or have an idea what the equation is, but they did not give us the equation. So when we look at a graph, we know it's a polynomial function if the graph is smooth and continuous. If the graph is smooth and continuous, then we know we're dealing with a polynomial function. Okay, let me talk to you about that word smooth. Smooth means there are no sharp turns. Okay? So this first one here is an example of a graph that's not smooth. It's going along perfectly smooth, but all of a sudden we get to this spot and we go, and it's a sharp turn to come to the other region, okay, to draw the downward curve. This is not smooth. Since it's not smooth, it is not a polynomial. Now, I bet, based on your experience in Chapter 2, that you already know what type of equation produced this. And hopefully you recognize, oh, that's an absolute value function because it's a V shape. Now, it did get flipped upside down, which probably means there was a negative out in front of it, but it's an absolute value equation. Absolute value equations do not match this polynomial format that we needed up here. Notice that all these polynomial functions up here, they never once had absolute value signs in them. So this was not a polynomial function, and the criteria that the graph is breaking is that it's not smooth. Okay? Compare that to the second graph. This graph, it goes up and it comes down, same as the absolute value one did, but this one is smooth. It's going up and then it turned. It didn't zigzag, real sharp turn like we did over here. So this one is smooth and it's also continuous. Okay, so I'm going to label this as a polynomial. And then let's talk about that word continuous. Continuous means that you can draw it without picking up your pencil. If you can draw it in one smooth motion without picking up your pencil, it's continuous. So notice I could draw this whole parabola here, this quadratic, in one motion without ever picking up my pencil. So it was smooth and it was continuous. It's a polynomial. The third one. The third one is smooth. There are no sharp turns. I draw this part, I draw this part. It did not have any sharp turns. It's smooth. But it's not continuous because if I drew it, I could draw this part, but then I'd have to pick up my pencil and bring it over here to draw this other part. So this one is not continuous. Because it's not continuous, it is not a polynomial. Okay. Now, just so you know, it was graphing along here, and it zoomed up, and then it skipped over a region. On the other side was zooming down. The kind of equations that produce that picture are when you have an x in the denominator. Okay, and we call these rational functions. So a while ago when we had these x's in the denominator of these equations here, that's our clue. Hey, it's not going to be a polynomial because when we graph it, you're going to have these breaks in continuity where you draw and then you have to pick up your pencil and draw the other region. Okay, this last one. It does seem smooth. There are no sharp turns or zigzags, and I can trace the whole thing without ever picking up my pencil. So this one is a polynomial. Okay? So hopefully you can look at equations and know whether you're dealing with a polynomial function or not, and hopefully you can look at a graph and know whether or not you're dealing with a polynomial function.